Determine which of the following sets are subspaces of R3, and there's 5 to determine. So let's understand the problem. First we need to know what subspace is. So here's the definition. A set V is a subspace of Rn, if it's in Rn, when the 0 vector is in V, if U and V are in V, then U plus V is in V. That's called being closed under vector addition. And 3, if U is in V and C is in R, then CU is in V. That's called being closed under scalar multiplication. Alright, so exactly what do we have to do here? It says to determine which of them are subspaces. Well, it doesn't say to prove. So that means I'm allowed to use other facts that I happen to know about subspaces. And there's 2 particular facts I think that might be useful, which are ways of constructing subspaces that are always guaranteed to give a subspace. So let me write them down too. If V is the set of solutions to homogeneous linear equations, then V is a subspace. And if V is the span, so the set of linear combinations of some vectors, then V is a subspace. Alright, so I've got the definition and I've got these 2 useful facts. Hopefully they will help me to decide if I have subspaces or not. A. The set of x, y and z in R3 such that x plus 2y is equal to 3z. Well, it's certainly a linear equation because there's no x squareds and no x times y's or anything like that. Is it a homogeneous linear equation? Well, homogeneous would mean that there's no constant term, or I could rearrange it to get everything equal to 0, and I can do that. Let me actually be absolutely clear about that. I can rearrange this so it's x plus 2y minus 3z is equal to 0. So this above set there is the same as this set. The set of x, y, z in R3 such that x plus 2y minus 3z is equal to 0. This is a subspace since it is the set of solutions to a homogeneous linear equation. B. The set of A, B, C in R3 such that A and B and C are all greater than or equal to 0. Well, it doesn't look like a subspace. That's not a linear equation. And it doesn't look like it's the span of anything, so I actually don't think it's going to be a subspace. So I'll run through the rules and see which one breaks first. Let's first see if the 0 vector's in there. Well, 0 and 0 and 0 are all greater than or equal to 0, so the 0 vector is fine. What about vector addition? Okay, well, my set is all the points with positive coordinates. And if I've got 2 points with positive coordinates and I add them, it'll still be positive, so it's actually closed under vector addition. That must leave scalar multiplication. Okay, well, multiplying something that's all positive by another positive number will still be positive, but if I multiply it by a negative number, I'll get negative coordinates, and that won't be in the set anymore. So it's actually not closed under scalar multiplication, and I just need an example to show that it's not closed under scalar multiplication at least once. So let me pick a vector that's in there. What about 1, 1, 1? The vector 1, 1, 1 is in the set, but -1 times 1, 1, 1, which is equal to -1, -1, -1, is not in the set. So the set is not a subspace, since it is not closed under scalar multiplication. Okay, part C. The set of 0, alpha, alpha plus 1, such that alpha is in R. It's a bit more difficult to tell. It looks like it might possibly be the span of things, because it's made by producing certain things in the coordinates of a vector, but I actually don't think it is, because it should all still be homogeneous linear equations, and that third one's got a +1 in it. So I actually don't think that it is a subspace, so I'm going to attempt to break the rules. Well, let's just see if the 0 vector's in there. The only way to do that is to attempt to write it as 0, alpha, alpha plus 1. So if 0, 0, 0 is equal to 0, alpha, alpha plus 1, then 0 equals 0 for the first coordinate, 0 equals alpha for the second coordinate, and 0 equals alpha plus 1 for the third coordinate. Well, that would mean that alpha is both 0 and -1 at the same time, which it can't be. So no solution for alpha. So 0, 0, 0 is not in the set. Therefore, the set is not a subspace. Okay, D, the set of A, 1, 0, -2, plus B times 5, 5, 7, such that A and B are in R. This one's much more promising, because look, this here is a linear combination of these two vectors. And since I can choose any A and B that I like, this set is actually the set of all the linear combinations of those two vectors, which is what span is. So this is actually equal to the span of 1, 0, -2 and 5, 5, 7. So therefore the set is a subspace, because all sets that are the span of vectors are subspaces. That leaves part E. E, the set of K, M, N in R3 such that K squared is equal to N squared. Well, again, it doesn't look like a subspace because that is a quadratic equation. So I'll run through the rules and see what breaks first. 0 vector is fine because 0 squared is 0 squared. What about scalar multiplication? I think that one actually might be okay. Let me try it. What we'd want to show that is if CK, CM, CN still satisfied the same equation? And I think it does, because if k squared is equal to n squared, then c squared k squared is c squared n squared, so ck squared is cn squared, so the formula works for my new point. So it actually is closed under scalar multiplication. Alright, so it must be the vector addition that's the issue, unless of course it actually is a subspace, but as I said, that's a quadratic equation and I don't think it is a subspace. So vector addition. If it's going to break under vector addition, then I just need to pick two vectors that are in the set so that when I add them together, they're not in the set anymore. Well, I can think of a perfectly good vector that is in the set. 1, 0, 1 is in the set, since 1 squared is 1 squared. And 1, 0, minus 1 would be in the set too, since 1 squared is minus 1 squared. But when I add them together, I get 2, 0, 0. And 2 squared is not 0 squared, so that's not in the set anymore. Is not in the set, since 2 squared is not equal to 0 squared. So the set is not a subspace, since it is not closed under vector addition. And that's the end of the problem.